Okay, one more here for the section. This is an example of a differential equation, and we want to show that this power series is a solution to this differential equation. Okay, so we're just going to find our derivatives, substitute into the equation, and see if it's true or not. So let's start off over here. We need now there's two ways you can do this. You can leave it in closed form and differentiate this term in general. You gotta be careful with your indexes when you do that. So in other words, I'll show you what I mean. If we take y prime, we're going to have this. We need a 2n and an x to the 2n minus 1. Down here we have a 2n factorial. Now, notice if you let n be 0, you're going to get a 0 here because of that 2n. So that first term really doesn't exist. And now also that we give you a negative exponent, so it's not going to be n equals 0. But before you do that, you can change this. Well, I want to reduce it first of all, because it's 2n over 2n factorial actually becomes negative 1 to the n, x to 2n minus 1, and this 2n, down here we'll have a 2n minus 1 factorial. And the 2n cancels with this 2n. You remember how to do that. You'd have to expand it. You have a 2n and then a 2n minus 1 factorial like that. So you get rid of that and you just have this. Okay, so now this doesn't make any sense at all to have a negative 1 factorial for us. It's not defined for a negative 1. So you can see that we don't have a first term here. This really should be written this way. So this is where it gets a little tricky when you try to differentiate these in closed form like this. So we have a 2n minus 1 factorial, like so. And our first term would be x to the first power, and we'd have a 1 here. So over here, notice your x is to the 0 power up in here. So I would not recommend doing it this way just because it gets confusing as to where the index is. And it's unsure. Let's put it that way. But let's look at this for now. Let's expand this. Let's write out the first few terms of this. We would have it looks like just a 1 minus, we have an x squared over 2 factorial, and then plus, looks like an x to the 4th, or 4 factorial, and minus x to the 6th, etc. So that would continue on. And if you differentiate these terms one by one, you would end up with, we're assuming there's a positive radius of convergence for this function, that we are allowed to do this, although we're not finding that radius right now. We'll assume that it's okay. So we'll have a 0 here, finding the derivative. Differentiate, we'll have a 0, we'll have a minus 2x over 2 factorial, and plus 4x to the 3rd, and minus 6x to the 5th, etc. Okay, now that's the same as negative x over 2. Whoops, sorry about that. It's not a 2. It's negative x. Next one is x to the 3rd over 3 factorial. Next one is x to the 5th over 5 factorial, and so on. Now notice what we have over here. Let's compare this result to this result. at n equals 1, we would have, expanding here, we'd have a negative, we'd have an x, and underneath here, we would have 1 factorial. The next term would be plus, we square the negative 1, 4 minus 1 is 3, and we have a 3 factorial underneath here. Notice that it is lining up with what we have over here. Okay, so rather than take your chances with this method, which seems like a lot of extra bookkeeping, so to speak, to determine the proper index after your operation, what you could do is just immediately expand this to a few terms, start differentiating, and leave it at that. Okay, so that is y prime. Now let's take a second derivative. We have a negative 1. We would have a plus 3 x squared over 3 factorial minus 5x to the 4th over 5 factorial plus etc. And that can be reduced to this. Minus x to the 4th over 4 factorial, etc. Now, we're trying to find out if y double prime plus y equals 0. Well, here's y double prime. And here's y up here. Notice they are the same, except opposite. So when you add them, yes, you will get a 0. Okay, now to do that with these closed forms is much more difficult. We probably shouldn't waste time computing that and working on that, but your second derivative in here would be, we'll start with a 1, we'll see if that's okay. We can check it. This would be 2n minus 1, and an x to the 2n minus 2. That, and you have a 2n minus 1 factorial, which then can be lowered down. I think I might just leave it like, well, this is at the 2n. So now your problem would be to, let's see, a second derivative, so this is a negative 1. Yeah. Your problem would be that you'd have to show, you would have to add this to this and show that they're equal to 0. So that is a job in itself. Some algebra to add these. And you'd have to, you could expand them if you wanted to and then show that the terms cancel out. Or you could join them together as one series. But you'd have to make sure the indexes were correct and matching. They both start with n equals 1, so that's good. And they both start with x, let's see, 1, that's x to the first, and that's not x to the first, that's x to the 0. So you'd have to do some adjusting to get these to go together. Too much work. So we wouldn't spend the time on that right here.